we have discussed the standard states, and we discussed standard state as the state of a substance when it is in its pure form, temperature can be any and pressure has to be 1 bar. However, in biological systems, the biological standard state is chosen in a different way, and we will discuss the details of biological standard states in this chapter. So, in this lecture, let us discuss what is a biological standard state. The conventional standard state for hydrogen ion, if we were to write in solution, will be when activity of hydrogen ion is equal to 1. That is the conventional standard state for hydrogen ion. Now, if activity of hydrogen ion is equal to 1, how do we define pH? pH of a solution is minus logarithm base 10 activity of hydrogen ion. Most of the times we simply write this as concentration. Please remember that it should be activity, not the concentration. You can only replace activity by concentration if the solution is very, very dilute. Now, if we put activity of hydrogen ion here as 1, that means pH will become 0, and that does not make sense. So, therefore, biological standard state is defined in a different manner. Let us go to the slide. Biological standard state means pH of the solution should be 7. That means activity of hydrogen ion should be 10 raised to the power minus 7. So, if activity of hydrogen ion is equal to 10 raised to the power minus 7, and we have discussed earlier that activities do not have any units. So, therefore, we will not put any units with the activity. So, therefore, pH will be equal to minus logarithm of base 10 raised to the power minus 7, this is equal to 7, and that is what we call the biological standard state. pH 7 means the solution is neutral. So, therefore, we will also use a little different notations for the biological standard states. Let us go to slide. We will adopt dynamic functions as G with this special sign, H and S with these special signs. So, standard states, biological standard states for Gibbs energy, for enthalpy, for entropy, we will be representing by these symbols. We all understand the role of pH in biological systems, because in biological systems the proton, exchange of proton, release or absorption of a proton usually happens, and therefore the solutions are prepared in buffer, and buffer action is it will resist the changes in pH. So, let us consider a reaction which involves the change of hydrogen ion, or which involves the release or absorption of a proton. Let us consider this reaction: A plus new moles of H, and this is in equilibrium or forming a product. the usual way of writing reaction Gibbs energy, which is actually a slope of Gibbs energy versus extent of reaction, we have earlier discussed that this is equal to the difference in chemical potentials of the product and reactants. So it will be equal to chemical potential of P minus chemical potential of A minus mu times chemical potential of H plus. And it is these chemical potentials which will decide the sign of reaction Gibbs energy. Now let me assume a situation where A and P are in their standard states except H plus. I repeat, let us assume a situation where A and P are in their standard states except H. In that case, delta Rg will be equal to mu naught P minus mu naught A minus, this is the stoichiometric number, and in place of mu H naught, I will write mu naught H plus plus RT log activity of H plus, because we know that mu is equal to mu naught plus RT log A, that we have discussed in one of the previous lectures. From this step to this step, what I have said is, let A and P be in their standard state. So I will write their chemical potentials as their standard state chemical potentials. And I am not saying that let H plus be in the standard state, let it be general under any condition. So instead of mu, I write mu naught plus RT log activity of H plus. Now I will combine all the standard state quantities. So delta Rg is equal to mu naught P minus mu naught A minus mu naught H minus nu RT log activity of H plus. I will combine all these standard state quantities, and therefore I have delta Rg is equal to, this is nothing but delta Rg naught, difference in the standard state chemical potentials, and minus log activity of hydrogen ion. Let us write like this, plus 2.303 nu RT minus log base 10 activity of hydrogen ion. I have written this as 2.303 into log base 10. And let us remember that this is equal to pH, this is pH. So I will now write this equation as delta Rg is equal to delta R G naught plus 2.303 nu RT into pH. And when pH is equal to 7, that means when we are talking about biological standard state, then 7 multiplied by 2.303 will give us a relation. But this now, since we are talking about biological standard state, is equal to delta R G naught plus, this is 16.12 into nu RT. This is the equation that we derive. Please note here, since we are putting pH is equal to 7, therefore I am writing this as the biological standard state reaction Gibbs energy. This is the thermodynamic standard state reaction Gibbs energy. Nu is the number of hydrogen ions produced or released, because our original reaction was A plus nu times H aqueous, it is in equilibrium with P. That is what our original reaction was. So obviously when nu is equal to 0, when there is no proton released or absorbed, then both these standard states will be equal. Standard state reaction Gibbs functions will be equal. And if there is a proton absorbed or proton released, then the biological reaction standard reaction Gibbs energy will be different than the normal thermodynamic standard reaction Gibbs energy. And in biological systems, it is this which will determine whether the reaction will be exergonic or endergonic, because as I said, most of the biological processes involve release or absorption of a proton. Now let us go to the slide. For this reaction, A plus nu H plus going to product, we have developed this equation for the biological standard Gibbs energy of the reaction. This 16.12 comes from 2.303 into pH value of 7, and this equation can be used to get the value of biological standard Gibbs energy of reaction. Now let us once again consider this and quickly go through the steps that we used. First we wrote the reaction Gibbs energy, which is in terms of the chemical potentials. Then in the next step, we considered P and A in their standard states except H, and then we used the definition of chemical potential for H plus and substituted into this equation, and we eventually got this result, and at pH 7 this result converts into this expression for the biological standard state reaction Gibbs energy. Let us consider an example. Nicotinamide adenine dinucleotide. In the given reaction, we have the reduced form of nicotinamide adenine dinucleotide NADH, and NAD plus is the oxidized form, and this is the reaction. There is a proton involvement, and both NAD and NAD plus are biologically important molecules, and in fact NAD and NAD plus play an important role in the later stages of respiratory process. Therefore this reaction is very, very important. At blood temperature, that is 37 degrees centigrade, the standard reaction Gibbs energy is minus 21.8 kilojoule per mole. But here we will be interested in knowing the biological standard reaction Gibbs energy, which can be calculated from this reaction, this expression. We know the value of delta R G naught and we know how many protons are involved. It is one only. You substitute the value of R and T as seen in the next step, and overall value is plus 19.7 kilojoules per mole. You see, the biological standard reaction Gibbs energy is overall positive. Overall positive means the reaction is endergonic. Endergonic reactions are not spontaneous. Now let us take another example for ATP hydrolysis. This is an example of an exergonic reaction. Again, let us consider the blood temperature, which is 37 degrees Celsius. The calculations suggest that the biological standard reaction Gibbs energy is minus 30 kilojoules per mole. Minus 30 kilojoules per mole is a highly negative value. That means the reaction is highly exergonic. Exergonic reaction means it can drive non-spontaneous processes provided some enzymes are available which will catalyze those reactions. And also, if we look at on the slide, that the hydrolysis of ATP is exothermic in nature, and entropy is also quite appreciable, which is plus 34 joules per Kelvin per mole. Whenever you have a large value of entropy change, that means the reactions are highly dependent upon temperature. Temperature is one of the factors which will affect the values of entropy change. And since this delta Rg, that is the biological standard reaction Gibbs energy, is very negative, and the hydrolysis of ATP thus we can label as highly exergonic, that is why this ATP phosphate bond is called high energy bond. The energy produced or the reaction is so highly exergonic that it can drive the other endergonic processes. It can drive the other non-spontaneous processes. Now let us discuss another question on the pH. The question is, calculate the pH of 0.15 molar ammonium chloride aqueous. The activity coefficient of a univalent ion in a solution of 1:1 electrolyte of this concentration is about 0.6. An easy question. We have to calculate the pH of ammonium chloride, and the concentration of ammonium chloride is given. In the beginning of the lecture, we defined pH as negative log base 10 activity of hydrogen ion. What we have is ammonium chloride. Ammonium chloride means we have NH4 aqueous, and upon interaction with water it forms NH3 aqueous, plus you have H3O So this is the due to the proton release. NH4 plus is weakly acidic. And in fact, we have in the question which is given to us has ammonium chloride. Chloride ion is not that appreciably basic moiety that it will affect the pH. Ammonium ion is very weakly acidic. Weakly acidic means the pH of the solution is going to be less than 7. And based upon this equation, we want to calculate the concentration of H3O, and if we know the concentration or molality of H3O plus, then from the activity coefficient we can calculate the activity. So let us write down an expression for its Ka, which will be activity of ammonia, activity of H3O plus, activity of NH4 plus. Water we take as 1. And activity is equal to activity coefficient into molality. For pure ammonia, this ammonia we will consider activity to be equal to its molality, and for these the activity coefficients will cancel out. So that means in fact in this expression we don't need to consider activity coefficient, because these will cancel out assuming that the activity coefficients are same for those. So I will write in terms of molality. Molality of H3O plus square, because the concentration is same, it is 1:1. So molalities are equal, divided by molality of NH4 plus, and I will also put M naught. M naught is 1 mole per kg because it is to be made dimensionless quantity. So therefore I have molality of H3O plus will be equal to Ka into molality of NH4 plus into M naught raised to the power 1/2. So I can easily calculate the molality of the proton or H3O plus. Let us now take a look at the slide. We are talking about this reaction and the acidity is due to this H3O plus, and we just derived this expression, we wrote this expression in terms of molality, and then since we equated this molality of ammonia equal to H3O plus, we eventually came up with this expression. Now you substitute the value of Ka and the molality or molarity of ammonium chloride is given. Once you put that, in fact let us consider this as molality, not molarity, this molality, mole per kg, because we have expressed in terms of mole per kg. So once you substitute, the answer comes out to be 9.2 into 10 to the power minus 6 mole per kg. But this is molality and we need activity. Activity is equal to activity coefficient into molality divided by M0. Again, M0 is introduced here to get rid of the units. we are given the value of activity coefficient, which is 0.6 into molality, and overall activity is coming to 6 into 10 to the power minus 6, and when you substitute into the pH equation, pH is minus log base 10 activity of H3O plus, the overall value comes out to be 5.2. And that is what I said in the beginning, that being a very weak acid, it will be lowering the pH of water from 7, pH will be less than 7, and therefore what we got is the pH value of 5.2. And the point to be noted in this question is that we were given 1:1 electrolyte. And if you note down here, the value of activity coefficient at 0.15 mole per kg is 0.6. 0.6 is quite different from 1. That means in case of electrolyte solutions or the solutions containing electrolytes, we cannot ignore the values of activity coefficient. We have to use activities. Even for a very, very dilute solution, the activity coefficient can be different than 1. And the activity coefficient can be calculated from the Debye-Huckle theory, and if the solution is very, very dilute, one can use Debye-Huckle limiting law. We will discuss Debye-Huckle limiting law a bit later, but I will just express an equation representing Debye-Huckle limiting law, which is log base 10 gamma plus minus is equal to minus A into Z plus Z minus root I. I is ionic strength, is equal to half summation I Mi Zi square. M is molality, Z is charge on the ion, and A is a weakly temperature dependent constant, very weakly temperature dependent, and gamma plus minus is the mean ionic activity coefficient. So this one is Debye-Huckle limiting law. Limiting law means applicable at very, very dilute molality. So while finding out the pH of a solution, especially in electrolytic systems, we must account for the activity coefficient, and that will give us the correct result. So in today's lecture, we covered two important properties for biological systems. One is pH, because pH is very, very important for biological systems, and second is the biological standard state Gibbs energy and its connection with this driving force or its connection with the exergonicity or endergonicity of the reaction, which drives, if it is exergonic, it can drive the non-spontaneous processes. So I hope the concept of equilibrium and equilibrium constant is clear, and we will solve several numerical problems based upon the equilibrium constant and the effect of external pressure or effect of changing the temperature, so that the discussion on the equilibrium constant and the concept of equilibrium constant and equilibrium becomes more clearer. Thank you very much.